bundles. We saw tangent bundles last time when we were talking about embedding, the Whitney embedding theorems, and like Gilman and Pollack mentioned very briefly what a tangent bundle is. They didn't go into much details or rigor, and I just mentioned that tangent bundles can be conceptualized as like disjoint union of tangent spaces for each point in the manifold. That's really vague. So we'll first develop what a fiber is, what a fiber bundle is. Then we'll probably see a bit of vector bundles, and then we'll see how tangent bundles are a type of vector bundles. And probably that'll be a better way to wrap this up. We'll go back to vector bundles in more detail in next month around, but yeah. Any questions before we start? Great. So if you follow the readings mentioned were Braden's section 9 on tangent bundles and section 13, and they're very brief. They don't really cover a lot. That's because, as I was saying for everyone join, that Braden is mostly doing the early chapters as a supplement to the more advanced chapters. But still, nonetheless, if you have gone through those sections, can be helpful. Also, I would like to know how many people here are seeing like fiber bundles for the first time. If they've seen something else similar in differential geometry. Okay, yeah. Gunjit is seeing for the first time. Okay. I'll try to make it as self-contained as I can, but you'll probably want to go more into it on your own. But yeah. Okay, so I'll start with what bundle is, right? So a bundle is basically triple. So you have three things. You have two topological manifolds. One of them is called the total space, and one of them is called the base space. And between those two topological manifolds, you have a continuous surjective map that goes from your total space to the base space, right? So if you denote the total space with E and the base space with M, then you have this surjective continuous map called the projection map taking you from E to M. And this whole construction, let's say, is called the bundle. Right? And this is a bundle of topological manifolds. Most of the time we'll be talking about manifolds that are C-infinity, that is, they are smooth. But here we can just say that those are just topological manifolds. Similarly, we'll have some other terminology which you probably have seen. You must have seen this before. What is a fiber? So if you have a bundle and you take a point in the base space and then you look at its pre-image with the help of this projection map, right? So you go up and see what is in the total space, the pre-image, and that is going to be the fiber for that point P, right? So it's the fiber, as you can expect, is going to be the set of points in the total space that get mapped to P, using the projection map, of course. So that's the basic terminology for what a fiber is and what a bundle is, and we'll see a bit more on that. There are many examples of what a bundle is. We'll see also what bundles can be like, but one of these examples is the product bundle. So if we have two manifolds and you take their Cartesian product and you have the Cartesian product as your total space, and you have one of them M as the base space, and you have the projection map, and the projection map is defined, as you can expect, is by taking an order pair PQ and mapping it into P, and this is going to be continuous and surjective, as you would expect, and thus is a bundle, but is the product bundle, right? Defined on the product. There's more about product bundle that we'll probably see later, but this is the structure. Yeah, in a bundle, if you have different points, they are going to be like mapped to different fibers, right? In the same bundle. So if you have a bundle from E to R, the real line, then you look at the pre-image of some point P, and that could be homomorphic. So this is the notation for homomorphic to S1 if P is less than 0. It's going to be homomorphic to the singleton P if P is equal to 0. And if P is positive, then it'll be equal to the unit interval, like in the real line. So this is just a case where if you take a point in the base, you'll have different things in the fiber. Now what is a fiber bundle? Okay, so we saw a bundle, but if we try to again like change the construction a bit, we can get a fiber bundle. So for a fiber bundle, you already have a bundle, and you take another manifold F, and you say the bundle we took is a fiber bundle with this specific fiber F if for every point in the base space the pre-image of that point is homomorphic to the fiber, right? So this is kind of unintuitive, like counterintuitive at first, but you kind of have to see this as a generalization of what a fiber is, roughly speaking. So you have a bundle, you take another manifold, and you say this manifold can act as a fiber for this bundle, right? So this bundle is called a fiber bundle with this fiber if you take each point in the base, you look at its pre-image, and the pre-image is always isomorphic to the fiber manifold we had. And yeah, diagrammatically you can represent it like this. And in the product bundle, the fiber bundle is going to be N, as you can guess. Right? We have this. So if you look at each pre-image, it's going to be isomorphic to N. Okay, so then another example is the Mobius strip. So the Mobius strip is a fiber bundle with this fiber which is the unit interval. So you have the fiber bundle going from the Mobius strip to the circle, and the base space is actually not equal to S1 across 0, 1, right? The unit interval. Essentially saying that you can't write the Mobius strip as a product bundle. It's not a product bundle. It is, but it's a fiber bundle. So that was another example. Further, we can see that further we can see that if you have a complex line, right? So if you have this C line bundle over M, and that can also act as a fiber bundle with that complex line as the fiber, right? But if you have the product bundle with the complex line, that is M cross C, then this time this bundle is over M, right? This time the fiber is over M, is M. Yeah, so yeah. Okay. So I hope everyone is clear on what a fiber, a bundle, and a fiber bundle is before we move forward to what sections are. Actually, I'm just like putting the terminology down. After that, I'll go into specific books and references to see more examples, and I will discuss more. Okay, moving on. So if you have a bundle, you have a map going from M, from the base space to the total space, is going to be called a section or a cross section of the bundle. If you compose this map, which is here sigma, with the projection map pi, and you get the identity over the base space, right? So sections are kind of like they're not inverses, but it's like is the map in the opposite direction, which when composed with the projection gives you identity. And we'll see later how in the case of tangent bundles the sections are actually vector fields, right? It's not going to be explained now, but we'll probably, if I have time, I'll get there. So what the section does is the section is a map which sends each point P to some point in the fiber, right? So essentially you have a point in the base space, you take it to the fiber, and then the projection map takes it from the fiber back to the point, giving you the identity map. So if we look back to the product bundle, then the section of this bundle is going to be this map, which takes every point in M and gives you an order pair P, comma S of P, where S is of course any section from M to S is any map from M to the fiber, right? So it gives you an ordered pair of the manifold with the fiber. So this is your product bundle. So that's what a section is. Then some more definitions. A subbundle of a bundle is going to be another triple where your total space, the new total space, is going to be a submanifold of the original, and same for the base space is going to be a submanifold of the original manifold, and the new map, the new projection map that you have is going to be just the original map restricted to this submanifold of the total space, right? So this subbundle, which is E prime, pi prime, and M prime, is a subbundle in the sense E prime is a subset of E, M prime is a E prime is a submanifold of E, M prime is a submanifold of M, and pi prime is just pi restricted to E prime. Something similar is also when like this is a subbundle, but like less stronger construction is if you have a bundle and you take a submanifold of the base space and you restrict your bundle to that specific submanifold, then you have a restricted bundle, right? So if you have a submanifold, you can have another bundle where your projection map is just restricted to the pre-image of the submanifold, right? So yeah. Now how do maps work between bundles? So I'll give some more terminology about bundle morphisms. So if we have two bundles, E pi M and E prime, pi prime and M prime, are two bundles, and you take U as a map from E to E prime, V as a map from M to M prime, then the pair UV can be called a bundle morphism if you have the whole diagram of the bundles commute, right? So if I zoom, you should have this diagram where this one is a bundle, this one is a bundle. You're going from here to here with U and here to here with V, and if you can make this whole diagram commute, that is, this holds, then the pair UV is called a bundle morphism. Right? Yeah, so another special thing about bundle morphisms is that the pair is actually unique. So if you fix U and you change V, they're actually always going to be equal to each other. So that's what it says here. If UV and UV prime are both bundle morphisms between the same two bundles, then V and V prime are going to be equal. Now, as you can expect, we're going to have some kind of equivalence, not relation, equivalence kind of mapping, right? Isomorphisms. So if you have two bundles, then they can be said to be isomorphic as bundles. If you have two pairs of bundle morphisms, UV and their inverses, and they satisfy the diagram as one would expect, right? So you have U and you have the inverse in the opposite direction, V, and V inverse in the opposite direction, and the bundle morphism essentially makes the two total spaces and the two base spaces isomorphic, right? So UV is called a bundle morphism, and we write this bundle is isomorphic as bundles to this bundle. Of course, this is just notation. I'm not sure if this is like very ubiquitous between writing isomorphic bundles, but yes. So that's morphisms and isomorphisms between bundles. Now we talk a bit about a few more intricacies. So a bundle E from E to M is said to be locally isomorphic as a bundle to another bundle if you take all the points in the manifold base space M, and you have a neighborhood of that such that when it's restricted and you get the restricted bundle, that becomes isomorphic to your this bundle. So if I explain, we have this as the original bundle, and we want this to be locally isomorphic to some other bundle. So what we do, well, we take a point in the base space, we have a neighborhood around it, we restrict our bundle to that, and we restrict it by precisely taking the pre-image of the neighborhood and mapping using pi restricted to that pre-image, and you get the neighborhood, of course. And this is the restricted bundle, which is going to be isomorphic to the bundle which we want it to be isomorphic, which is this one. This is basically giving you a local case of isomorphism between bundles. There's something else that happens locally between bundles, something called local triviality. So a bundle is going to be said to be trivial if it's isomorphic to its, not its, like a product bundle, right? So if your bundle can be can have isomorphism to a product bundle, then it's trivial. And a bundle is said to be locally trivial if it is locally isomorphic to a product bundle. So that if you restrict your bundle, then it's isomorphic to some product bundle, making it locally trivial. And the examples are that the cylinder C is trivial as a bundle, and as it is trivial as a bundle, it is also locally trivial, because you can, if you remember how you get a cylinder, right, is the product of the intervals, and you have a bundle there. That's why if you look at it locally too, you can have a local isomorphism to the product bundle. The Mobius strip, on the other hand, is not trivial in general, but it is locally trivial. And a very intuitive way to think about this is that the Mobius strip locally actually looks like a cylinder, right? But if you like zoom out, that is to say, you look at it in the general case, it's not a cylinder because of the twist you have, right? The change of orientation. So it's not locally trivial, but it's not generally trivial, but it is locally trivial because, as I said, it locally looks like a cylinder. Does that make sense, or do you have any questions? Because I pretty much uttered a lot of terminology into you. Not sure if everyone has digested that. But if you have questions, we can discuss. Mm-hmm. Everyone good with it? Well, I don't know. Maybe I'll ask something. Um, why do you think the Mobius strip locally looks like a cylinder? It gave like a very brief hint, but still, I would like an explanation. Why does it look like a cylinder locally?
Uh, if we take a point, the Mobius strip,
Mm-hmm.
uh, then along the strip, if I take a small uh, section of the strip of say height
Mm-hmm.
h, then uh, then I think it's homeomorphic to a square,
Okay.
and that product of it looks like r square, which can be considered as a trivial bundle.
No, I'm asking like wait, you pretty much said it. Like so it is locally looks like a cylinder, right?
Yeah,
Okay,
yeah.
yeah. As for sections, we don't require any regularity on the map section. No, I don't think yet we need. Yeah, I think you can have sections without regularity. I'll have to probably confirm, but yeah, you don't need it. Okay. Yeah, we'll be focusing mostly on smooth sections. So that uh, was our trivial bundle is with locally trivial bundle is. We'll have some kind of operation within bundles again. Pullback and pushback. If you've seen pullback and pushback of smooth maps and manifolds, probably know what it is. But yeah, if you have a bundle and you have this map from M prime to M, then the pullback of this bundle induced by this map is defined as another bundle where the total space is defined in this manner, right? So probably stare at that for a while if you haven't. But that's the pullback. So what it does is it takes this map that you have from M prime to M, and it says, okay, we'll have another E prime where we're going to take pairs little m prime with E, which would be in the Cartesian product of M cross E, and the condition is that all of these little m primes get mapped to the image of E's, right, over the projection map. So what it is saying is that m prime using f gets mapped to the same place where little e gets mapped to using the pi, right? So essentially, it's like using this f as kind of like, very roughly speaking, is a substitute for how to move things from m prime to the base space, um, and this is a pullback. So that's what it does. This is your E prime, and the new projection map that you have, that is your pi prime. What it does is it takes these order pairs and it gives you little m prime, right? Like, like the projection. Um, so Yeah, so that's your pullback. So if you have this as your pullback bundle of this bundle induced by this map, then one can easily construct a bundle morphism, yada yada. Then that's pretty obvious. If you have this pullback of this bundle, then you get an obvious bundle morphism, which is from E prime to E, taking these order pairs and giving you just E. And here instead of UV, you just have the usual F. This is another thing that sections on a bundle pull back to the pullback bundle. So essentially, your sections stay sections, right? If you pull back them using the pullback bundle, then they're still sections. So it is sorry, it is not that hard to see. You'll probably have to do some diagram chasing to see that this works. But if you remember from differential geometry, if you have done that, there's this maxim that they called is that vectors are pushed forward and covectors are pulled back, right? Or something very similar. I'm not sure if there's a variation of it, but this is one of the maxims in differential geometry. So smooth sections, so here sections are kind of like covectors that get pulled back. And how do they get pulled back? Okay, we can see that. So you have E, M, this is a bundle with sigma as its section. You have this as the pullback bundle from F, and your section here is sigma prime. And you have to just show that sigma prime and sigma are the same thing. And so using this is a bundle and this is a map, so you have a obviously a map from M prime to E, which is sigma circ F, and what this does is actually you just have to show that sigma sigma prime like I'm probably missing my diagram chasing. Yeah, basically you have to show that they both give you sigma. So okay, wait. Okay, yeah. So sigma circ F determines a map from M prime to E, which sends each little m prime to sigma of F of little m prime, which is in E. Yeah, yeah. But sigma is a section. Oh, yes. So sigma is a section. If you apply pi to it, you're just going to get the identity map for free. So pi applied to sigma circ F gives you F of M prime. So what this means is that M prime with sigma circ F of M little m prime is actually in E. That's how we've defined E prime. Right? So what you do, well, you apply this under the other projection map on this side, right? Pi prime. And what you get is M prime, because that's what pi prime does. It just gives you this component. So you get little m prime, and so what this does is sigma prime is going to be from m prime to this, and like this obviously is a section, because if you compose it with pi prime, you're going to get the identity on m prime. Yes, it's going to be a section. So yeah, so essentially saying that sections get pulled back to sections. So that was our kind of terminology that I wanted to give for today. Next, we'll go from a few books to get some more background on bundles. Before I leave these notes, any question?
Are these notes like posted on the Google Drive also?
No, these aren't. I'm still in the process of writing and making them nice enough. I probably would try to make them available by tonight. It's just a lot of work, so I'm not posting it without fixing all the typos. Yeah.
So these are your personal notes.
Yeah, these are the notes I'm making for the course.
Okay.
So that was what we needed to know for terminology. Now we'll see from a few books on what to do with this terminology, and we can see a few examples. So the books that I'll probably refer to are I'll show all of them. So they're in the schedule. They're presented. So this is PIVX Volume 1. Probably everyone knows. And the other book is this one is Jeff Willey's Manifolds and Differential Geometry. He has a great chapter on fiber bundles, which goes into a lot more depth that we need but he has some interesting examples that we might want to see. This is the Mobius band that I was talking about, but we'll see how exactly that works in this explanation. And other than that, I have this book, Mobius. I don't know how to pronounce his name, but his differential geometry. I knew it from this guy who did it in Oxford or something. And this is a very good book. It's like not that long compared to other books. It's just 300 pages, and he has several chapters dedicated to bundles. Right? So he has vector bundles for like 4 chapters just on vector bundles. So it is very detailed. And lastly, this is Wall's Differential Topology. This is one of the books that we'll be going through in the course repeatedly, and he has the first few sections in the first chapter dedicated to bundles. So yeah, you're recommended to go through these references if you need more depth. So I'll go through some examples of what happens. But before the examples, we can see what a vector bundle is. I didn't define what a vector bundle is, right? So we can see that if you have a manifold, a real vector bundle, so this is not the general definition, but this is like very specific to over R, that a real vector bundle over a manifold M of fiber dimension n in a smooth manifold E of dimension n plus m is actually a bundle which has these conditions, right? And these conditions are kind of important. So of course the first one is just the smooth map I, which we saw. This is the smooth section, right? Just weird notation, O hat. But this is the same thing because pi circle hat gives you the identity. Additionally, there's this smooth map mu from R cross E to E such that it satisfies these things. And what it satisfies is that pi of mu RV gives you pi of V. And just like a few like routine checks for the fact that this is actually well defined and works nicely over this construction. And the last thing that we need to check is that if you take a point P in the manifold, then you have a neighborhood U of that P, and you have a map which takes you from the pre-image to Rn, such that when restrict this map, which is like lambda u, to the pre-image of some x, then that gives you diffeomorphism, right? And that diffeomorphism works linearly with your vectors, real vectors, right? So this is a map from the pre-image of the neighborhood to Rn. This is another map that you get from the pre-image of just a point in the neighborhood, which gives you a diffeomorphism, and this map obeys this condition, which is lambda u of mu rv helps you not only get just have lambda u and v, but it pulls out the real vector, so it works quote-unquote linearly. Okay, a few more things to note. So this book actually doesn't start with fiber bundle, it starts with vector bundle, so it's talking about how this is actually a fiber and whatnot. But as you can guess, the kind of like operation that we were doing here with R using this mu was actually a multiplication operation, and that's what they say here. So the map from E to E given by V to mu RV is the multiplication by R. That's what this mu helps you with. So yeah, mu defines an action on E of the multiplicative group of the real numbers, so you can do that. And another remark is the O hat that we saw that I said is the section, is they call it here the zero section for some reason, but yeah, it is indeed a section. And this is how like local trivialization, local triviality that we saw works with vector bundles. So lambda u that we saw, which is like from the pre-image of an open neighborhood to Rn, this actually defines a diffeomorphism Pu, which goes from this E restricted to U cross Rn. This is a diffeomorphism, and what it does is it takes V and it gives you pi of V comma lambda u of V, and lambda u of V is we know how that works here. So this is a kind of more specialized way of looking at local trivialization in the case of vector bundles. So yeah, so these are a few things to know about vector bundles. That was real vector bundles, right? So if you look at like vector bundles in general, you have a few other conditions that you'd need. Yeah, here they probably define it in a bit weird way using the co-cycle constraint, which I don't think others use for vector bundles, or probably they use. But yeah, we can try going through this. So he says in this definition, a real vector bundle of fiber dimension n is given by the following data. First, a locally finite cover U of M. Then second, an assignment of a map G U prime U, which goes from U intersection U prime to GL and R. To each pair U and U prime in the curly U, subject to two constraints. First is that GU prime must be equal to GU prime U inverse. That makes sense. Second, if u prime and u double prime are any three sets, then from this curly u, with all of them being disjoint, none of them being disjoint, then the composition of these g's related to these u prime and u double prime gives you the identity. So it's a way of, right, so it's a transition function in some sense, and that's why I say the bundle transition function. It takes you from, in some sense, from this u prime to u, and this is the co-cycle constraint. Okay, I'm not too positive on this being very helpful, but this is kind of a peculiar way they're defining their instruction. So these are a few examples of vector bundles. One of them is the trivial bundle, which is the vector bundle M cross Rn over M, whose fiber is Rn. So this is an example of the product bundle, right? It's just that instead of N, we have Rn here, okay? And it's called the trivial Rn bundle. And I guess as we discussed, like why it is trivial is obvious, as we defined it is trivial bundle. What is the Mobius bundle? So if you try to have the like angular coordinates for the circle, right? So theta goes is like in the this 2 pi some real 2 pi times some real for the circle. So if you have S1 as the unit radius circle in the origin of R2, for an angle theta, gets mapped to the point cosine theta sine theta, obviously. So if you take E to be some submanifold in S1 cross R2, and you denote the subset of points theta with V1, V2, such that cosine theta times V1 plus sine theta times V2 is equal to V1, and the other way around, sine theta times V1 minus cosine theta times V2 is equal to V2. That's how you define this. And this actually defines a bundle over S1 with with fiber dimension as 1. And that is the bundle which gives you the Mobius band. I believe they're going to explain this a bit more later. But yes.
I can't picture what that condition means. That cosine theta v1 plus sine theta v2 equals v1.
I think they're using this cosine theta and sine theta as, you know, these what do you call it, coefficients for vectors, something similar, which like what it gives you is you define this v1 in here as the case when cosine theta v1 plus sine theta v2 gives you v1, and this gives you v2. So if you try to have this, it'll be probably sine theta v2 is equal to v1 times 1 minus cosine theta, right? And you'll get like the ratio v1 v2 for some sine theta and cosine theta. I think they're taking that subset of thetas. But I believe what this leads to with the Mobius band is it helps you getting vectors in the both orientation, probably. I wish they had a more graphical explanation for this. I'm not sure if they do later. No. But in this case, actually, this is Jeffrey, right? Yeah, Jeffrey Lee. He does the probably same thing, which he does without the kind of condition that we saw there. He's not using the trigonometric parameterization. So we can try this maybe? What do you think? So he's defining it the same way we did, 2 pi n. And he has this equivalent summation over R cross the open interval. And that gives you the familiar Mobius band. And he defines this projection from the Mobius band to the equivalence, so the quotient, of course, which is the S1. And what it does is it takes xt and it gives you x. So you have to show that this is a fiber bundle by exhibiting an atlas consisting of 3 bundle charts. Right. So here he'll probably check everything that we defined in the last book. So here if you see in the definition itself, he defined like the bundle transition function, gu prime, gu whatever. But here Jeffrey is checking it manually, right? So he's checking G1, 2, G2, 3 and all these maps, and he's checking that all of them are like well-defined bundle charts. So you have the bundle transition function. So I believe that's like the big picture of what he's doing. If you're interested, we can go into the details of this long construction. Oh, in the previous book, this one.
Yes.
It's the rotation. Yes. That was pretty dumb. This is the rotation matrix. Yeah, that's what I was kind of heading towards. It's the change of orientation. Yeah, right. That's the change of orientation. Yeah. So not many vectors are fixed by a non-trivial rotation. What is the base space? E is this. The bundle over S1, right? So they're defining it over S1. Yeah.
But the V's live in R2.
No, V.
Oh, V1 and V2.
V2,
The
yeah.
vector V1, V2 is in R2.
Yep.
Oh, so these are numbers, not vectors.
I mean,
It doesn't matter.
Yeah, in the real,
So
yes.
we're taking a rotation matrix, cosine, sine, negative cosine, and multiplying it by V1, V2. And we get V1, V2 back out.
Yep. It's interesting, like, probably one can, like, the way, like, 3 blue, 1 brown makes his videos, like, one can make this Mobius strip with, like, 2 vectors, and this rotation matrix, changes the orientation. That'll be nice.
But I mean, if this matrix really is a rotation, for non-trivial rotations, the only thing fixed is the origin.
Yes. I think, yeah, okay. Can you add the question? I think, yeah, you would have the non-zero rotations, sorry, non-zero solutions, but I'm not sure if it's needed. Line of solutions, I see.
Which book you are currently following? Is it named book or your notes, lecture notes?
No, this is Differential Geometry by Clifford Henry Thomas. I haven't shared this one, but yeah.
And one more thing, that all these books and this and your lecture notes, where these things will be uploaded?
The books, like, so if you go to the Differential Geometry of Manifolds chat, the pinned messages has a Google Drive link where all the needed books are there. Lecture notes would be uploaded very soon. It's just that I've been working a lot on it, so I need some time.
Thank you.
Let me post this book as well. Yeah, so yeah, it would have been like something like span of yeah, that makes more sense. I think the author is resisting linear algebra kind of terminology. It might be helpful. But yeah, so that was the Mobius band example. I don't know if people are interested. We could go into this very detailed instruction here. If people are interested, or I might just post screenshots from this these pages if people are interested in reading it later. That there are only two lines, line bundles of rest from Trivial and the Mobius bundle. Ah, yeah, that's a nice problem to think about. So yeah, I don't know if people are interested about this specific example. I'll post the construction in the chat. Yeah, so this is Jeffrey Lee, not to be confused with another Lee who has 3 books on all kinds of manifolds. So, yeah. Okay, so we did some vector bundles. We saw some examples. Let me see if I have some other interesting examples before we move on to tangent bundles. I guess not. So let's see what a tangent bundle is. So we'll see the tangent bundle from somewhere else probably for more comprehension. That will be Spivak. So Spivak very nicely gives you a very intuitive account of what tangent bundle is. It doesn't go very much into the abstract fiber bundle, but it tells you what tangent vectors are, what tangent space is, how this projection map actually allows for like these pre-images to be mapped onto a specific point. So this is what a fiber can be graphically represented with. So you'll have a point on Rn, you look at its pre-image in the tangent space, and that will be a fiber over the point. Now, if you remember, like what I said in the beginning, that last time we defined the tangent bundle to be the disjoint union of tangent spaces for each point in the manifold. And that's what it kind of alludes to. At each point, the fiber is specifically tangent space, right? So this is TRN, this is the tangent space of Rn, but it can be any other tangent space. So what happens is that here he's like going from the fiber to making this actually a like well-defined vector space. So it is a tangent space indeed. So he's defining the product here, the sum product, the operation, and is saying, okay, so this is actually a tangent space. But kind of like what we need is not really the nitty-gritty of this. Maybe you can go into like how to how to define these tangent vectors from curves, and the transition vectors, and transition maps and all of that. And it's very well explained, but I don't think we need to spend more time on that. But I rather want to tell you how this connects with the disjoint union thing, right? So what actually all of this construction is about is that every vector in a tangent space is the tangent vector for some. Here's an alpha. That's probably a curve. But yeah, so in the tangent space, every vector is a tangent vector. Right. So yeah, so essentially you get an n-dimensional subspace, which is the set of all tangent vectors for a specific point to smooth curves. And what happens is, if you take this, and I'm probably not lost on the notation. Okay, yeah, that's your I. I was just confused about what this I is, but yeah. So this tangent bundle, whatever it is actually can be defined as the disjoint union of all these tangent spaces. So these AMs are actually tangent spaces. And how this is a tangent space is actually, it's not exactly a tangent space because they're defining it as the subspaces of tangent space. So here, this is actually a subspace of I of M. So I is actually your chart map or whatever, cross Rn, and this is actually a subspace of the tangent space of Rn, right? So basically, of course, these are tangent spaces, but they're not really talking about it directly, but these are subspaces of those. So at each point P, you get this subspace, and you take the disjoint union of all of those, and you get this. And what you do is you have a projection map pi going from this disjoint union to M, the manifold M, and what it does is it takes a tangent vector and it maps it onto a point, right? So this is, if you recall, this is exactly what a bundle is. Right? You have a total space, you have a base space, you have this projection map, except instead of in our case, at each point in the base space, if you look at the pre-image, you get a very nice vector space called tangent space. That was not what it was in the general case of fiber bundles. So these are your tangent bundles. So this is another way. I think this is similar to what we were talking about, the cosine theta and sine theta. He's giving some examples for what tangent bundles can be. So if your M is actually just the S1, and you have the inclusion of S1 into R2, then you have this curve defined for the theta, which is equal to cosine theta sine theta, the same thing, and it goes through every point of the unit circle. So c prime of theta, the tangent vector, is going to be minus sine theta cosine theta. It can't be 0. Then take a point P, which is cosine theta sine theta. Then you look at UP. So UP is just the tangent vector at that point. Hopefully, yes. Minus sine theta cosine theta for that point. Then S1IP. So S1IP is like it's a vector space of all these tangent vectors, right? Multiples of UP. So this is what it looks like. And F1 of M goes from the tangent bundle. Again, the disjoint union of all these tangent spaces, and it maps it onto S1 cross R1, and it does it in a very nice way. so that this diagram commutes, basically. And this is a very good example of what a tangent bundle is. Yeah, there's this nice, this is a very nice thing in topology. I'm not sure if people have seen this before. It's a very nice theorem, but it's quite hard to prove that you can't actually comb. So if you have a sphere which has hair on it, right? So it's like a hairy sphere. If you take a comb and you try to like comb the hair on the sphere, you can't actually comb it. It's a very funny, but it's a very nice example from topology. Have people seen it before? If people have, then we might talk about it. Right. I mean, yeah. I think we'll see the proof later. When we do Pollack. Yeah, the hairy ball theorem is probably in Gilliman and Pollack. But it's probably taught in topology. I don't know. Yeah, it's a very nice thing, which was probably proved by Poincaré himself.
Yeah, it seems like it might need the differential part if we're going to talk about vector fields.
Right. It is like in very much it is closely related to the Lefschetz fixed point theorem. And also I think
Right.
what was the in the case of a sphere you can't comb it, but if you have like a hairy torus, you can comb it, right? Yes.
Easily.
Yeah, easily.
Page 134 of Gilliman has the Poincaré-Hopf index theorem.
Is that on the oriented section? Oriented and intersection theory part? Yeah. If your head were a donut, you could comb your hair without leaving a bald spot. Yeah, the Poincaré-Hopf indexing theorem, which is probably the important one. But yeah, I think Spivak is probably not going to talk about it in detail. I'm not sure. It's taking the S2. Yeah, he's not proving it. He's just showing that this is an example. Okay. Yeah, there are a few other things that I wanted to talk about, but not sure. Yeah, this is again for the Mobius strip. So you'll have to use the Howard theorem again to show that there is an appropriate homeomorphism, but the construction is actually interesting. So you have this TMI, the tangent bundle, to M cross R2, where M is your Mobius strip. The inclusion of M into R3, we know that it can't be included. We have the specific map, and at each point, right, you're moving between -1 and 1. Okay, so yeah, I don't think there's anything else specifically that I would like to talk about. You probably should do some more reading if you're interested, but we'll come back to vector bundles in more detail, like after a month, after we're done with transversality. So similarly, the preset for next week is going to be released today. I'll make it. I probably have this. I haven't made it. I probably have selected problems. It's not going to be from Pollock. It's going to be from other books that I refer to. So you I'll send the books if you need to look at the references. But yeah, the problems would be from them. Okay. So yeah, anything else before we end it today?
It's been a good day. I enjoy the geometric stuff.
Certainly, yeah, we did. I think we have got enough terminology with bundles before we make a deep dive into it. There's a lot actually to be in bundles that one can do, but we'll see how far we can go. Okay. So, thank you everyone for joining today. It was very nice. It was nice to have a new member too. And we'll meet Friday to discuss problem set 2. If you can solve any of the problems, solve them and send it over DM to me, and we'll discuss everyone's submissions on Friday. And the next PSET 4 will be out today for next Friday. So, yeah. Okay, have a great day, everyone. We'll meet next Friday. See ya.
Bye.